Take a look at the humble soybean. Today, it's the backbone of global agriculture, a multi-billion-dollar empire hiding in plain sight. But if you walked into a wild field 10,000 years ago and tried to eat these straight off the vine, your body would pay a heavy price. Plants don't want their offspring digested. To protect its energy-dense seeds, the soybean evolved a terrifyingly elegant chemical weapon. Trypsin inhibitors. Think of trypsin as the master key your digestive system uses to unlock proteins. The soybean's inhibitor mimics the exact shape of that keyhole. The moment it enters your stomach, it permanently plugs your digestive enzymes. Eat them raw, and your body completely loses the ability to process protein. Your pancreas works overtime, swelling, as it desperately tries to pump out more enzymes, leading to severe malnutrition and acute gastric distress. According to the FAO database on anti-nutritional factors, it is one of nature's most effective biological locks. And yet, humans turned this poison into a superpower. Before it became a global commodity, the soybean was a geographic miracle worker. It possessed a secret weapon below the surface, a symbiotic relationship with bacteria in its roots that literally sucks nitrogen out of the air and pumps it into the dirt. It didn't just adapt to poor soil. It healed it. For millennia, Chinese farmers used it in crop rotations to revive exhausted fields, transforming the yellow earth into a self-sustaining breadbasket. But by the late 19th century, this bean triggered a geopolitical gold rush. Western Europe was urbanizing fast, and its lands were depleted. It desperately needed fertilizer to grow food and cheap oil to lubricate its industrial machines. Manchuria had the answer. The region became the soybean kingdom, producing nearly 80% of the world's supply. This wasn't just trade, it was fuel for empires. Imperial Russia and the Empire of Japan realized that whoever controlled the Manchurian railways controlled the global flow of soybean cakes, the ultimate cattle feed and fertilizer that kept European cities alive. The competition over these bean fields became a major flashpoint, directly feeding into the tensions of the Russo-Japanese War and the later colonization of the region. A simple bean had become a geopolitical currency. So, how do we get around the poison? It started with an accident. Local legends point to Luan, an ancient Chinese prince, an alchemist obsessed with finding the secret to eternal life. He wasn't trying to cook dinner. He was mixing soy milk with various minerals like gypsum and seawater bitterlings, hoping to brew an elixir of immortality. He failed at making the elixir. But the chemical reaction did something else entirely. It curdled the milk, separating the proteins and washing away the water-soluble toxins. He had accidentally invented tofu. Centuries later, this bizarre bean caught the eye of another eccentric billionaire, Henry Ford. In the 1930s, Ford became completely obsessed with soybeans. He spent millions researching how to use them in manufacturing. He wore a custom-tailored suit woven from soy fibers, put soy-based plastics into his cars, and in 1941 unveiled the plastic car, a vehicle with a lightweight body made partially from soybean formulas that could withstand a blow from a sledgehammer. Whether through ancient alchemy or modern industry, the secret to taming the soybean always comes down to breaking its defenses. Humans eventually perfected a three-step neutralization strategy. First comes soaking, which leaches out a significant portion of the water-soluble anti-nutrients. Next is the critical threshold, sustained high heat, bringing soy milk or beans to a rolling boil at 100 degrees Celsius. For at least 20 minutes applies enough thermal energy to physically unravel the trypsin inhibitor's rigid structure. Its shape collapses, rendering it completely harmless. Finally, we use microbial fermentation, the secret behind soy sauce, miso, and tempeh. Microorganisms step in to finish the job, pre-digesting any remaining complex proteins and unlocking a wave of savory umami. By forcing the plant's chemical weapons to surrender, humans unlocked a massive shelf, stable strategic protein reserve that helps sustain whole civilizations. They are named after the very organ they resemble, looking almost harmless on a kitchen counter. But raw red kidney beans carry a defensive payload so volatile that eating just 4 or 5 of them can land you in an emergency room within hours. The weapon here is phytohemagglutinin, or Phe for short, a heavy-duty plant lectin. In the wild, this protein functions as a biological landmine for a plant's seed. When a mammal chews a raw kidney bean, the Phe doesn't just pass through. It targets the red blood cells, binding to the carbohydrates on their surfaces and forcing them to clump together in a process called agglutination, simultaneously. It tears into the delicate carpet-like lining of your small intestine. The body's reaction is immediate and violent. Acute projectile vomiting and severe abdominal pain, as your digestive tract frantically tries to eject the invader. It's an incredibly hostile chemical boundary line drawn by nature. Yet, despite this built-in security system, this lethal little capsule became one of the most widely traveled crops in human history. Long before it crossed oceans, the kidney bean was part of a brilliant agricultural trinity in Central and South America known as the Three Sisters. Indigenous farmers didn't plant crops in isolated, sterile rows. They planted corn, beans, and squash together in a single mound. The corn provided a natural trellis for the bean vines to climb. The squash leaves shaded the ground, acting as a living mulch to prevent weeds and conserve moisture. And the kidney bean, utilizing its underground network of bacteria, pumped vital nitrogen back into the soil to feed the corn. It was a flawless, self-sustaining ecosystem that allowed early civilizations to thrive without exhausting the land. When European explorers arrived, they didn't just find gold. They found this massive source of dense plant protein. As the bean spread across Europe via the Columbian Exchange, it completely altered the continent's social fabric. In places like Italy and France, where meat was a luxury reserved exclusively for the aristocracy, the kidney bean became known as the poor man's meat. It was incredibly hardy, cheap to grow, and could be dried and stored for years. During the brutal winters, crop failures, and endless continental wars of the 17th and 18th centuries, these stored sacks of beans kept the European working class from starving, quietly fueling the labor force of the early industrial world. But as the bean went global, humans stumbled into a bizarre modern paradox. In the 1970s, a strange wave of sudden food poisoning cases hit households across the UK and the United States. Perfectly healthy people were cooking wholesome bean stews and ending up incredibly ill. The culprit wasn't spoilage or bacteria. It was the invention of the countertop slow cooker. Here is the sinister catch with the kidney bean's defense mechanism. Phe is remarkably heat-resistant. If you cook kidney beans at a low simmer, around 75 degrees Celsius to 80 degrees Celsius, which is exactly what a standard slow cooker does on its low setting, you don't kill the toxin. In fact, science discovered that heating the bean to this sub-boiling temperature actually increases its toxicity up to 5 times. The mild heat breaks open the plant cells, releasing the toxin without destroying its molecular shape, turning a healthy dinner into a concentrated poison. Defeating this trap requires absolute, unyielding physics. To make a kidney bean safe, you have to follow a strict protocol that humans learned through trial, error, and survival. First, a prolonged soak in water leaches out a portion of the surface toxins, but the real execution blow happens at the boiling point. The beans must be subjected to a rolling boil at 100 degrees Celsius for a bare minimum of 10 minutes. That violent thermal energy is the only thing strong enough to physically shake the Phe protein apart, unraveling its toxic shape into a completely harmless, digestible nutrient. Once that threshold is crossed, the bean transforms. The interior starch gelatinizes into a rich, velvety texture, turning a defensive weapon of the Americas into the comforting, creamy anchor of a classic chili con carne, or a rich Mediterranean stew. Once again, humans weaponized heat, forcing nature's toxins to surrender to our dinner tables. Deep underground, nature hides some of its richest energy vaults. But if you were a starving gatherer thousands of years ago digging up a wild yam, your first bite would taste intolerably bitter, followed quickly by a burning sensation in your throat and severe stomach cramps. The defense mechanism here is a family of toxic compounds called saponins. Specifically, diosin, named after the Greek word for soap, saponins possess a unique and terrifying chemical property. They are natural detergents. Imagine a molecule that acts like a microscopic crowbar. The moment wild yam's saponins enter your body, they seek out the cholesterol in your cell membranes, locking onto it and ripping the lipid bilayer apart in your bloodstream. This causes hemolysis, literally bursting your red blood cells. In your stomach, it dissolves the protective mucus lining, turning an intended meal into a toxic, cell-destroying irritant. It's an incredibly aggressive way for a root to tell the animal kingdom to dig elsewhere. Yet humans didn't walk away. We stayed, cracked the code, and used this plant to rewrite human history, in more ways than one. Geographically, the wild yam is a survivor. While grain crops like wheat and corn are fragile and easily wiped out by surface fires, droughts, or passing armies, yams hide their treasures deep beneath the jungle floor. In the tropical yam belt of West Africa and the dense canopies of Mesoamerica, these tubers adapted to poor, acidic soils by locking away nutrients where no surface predator could reach them. They became a literal underground insurance policy against famine. But the wildest chapter of the yam's history didn't happen in a field. It happened in a pharmacy. In the 1940s, an eccentric American chemist named Russell Marker discovered that the exact saponins keeping wild yams safe from insects could be chemically converted into progesterone, the human hormone. Before this, hormones had to be painstakingly extracted from animal organs at astronomical costs. Marker traveled to Mexico, gathered massive wild yams, Dioscorea mexicana, and unlocked a cheap, abundant source of steroids. This triggered the historic Mexican yam rush. Suddenly, wild yam roots were more valuable than gold. They became the foundational raw ingredient for the invention of the birth control pill. The geopolitical stakes grew so high that the Mexican government eventually banned the export of wild yam roots to protect its domestic monopoly, sparking international smuggling rings, corporate espionage, and a global medical revolution that completely reshaped modern demographics and women's liberation. Long before modern labs capitalized on these compounds, pre-industrial societies figured out how to strip the yam of its chemical teeth using simple, brilliant physics. Because saponins are natural detergents, they have a critical vulnerability. They are highly water-soluble. Human ancestors developed a patient, multi-step detoxification protocol. First, they discarded the skin and outer layers, where the plant concentrates its highest payload of toxins. Next, they sliced the bitter flesh into thin strips and submerged them in woven baskets, placed directly into rushing rivers. Leaving the yams in running water for days literally washed the poison away, dissolving the saponins molecule by molecule and letting the current carry them downstream. To finish the job, humans applied prolonged heat, subjecting the leached yams to high-temperature boiling. A roasting completely breaks down any remaining heat-sensitive anti-nutrients. Once the saponin defense network is thoroughly dismantled, the wild yam undergoes a stunning transformation. The toxic, bitter root softens into a rich, velvety mountain of pure, digestible starch. It became a survival staple that could sustain populations for months on end by turning a toxic chemical deterrent into a clean slate of pure energy. Our ancestors proved that with enough patience and a little running water, even the jungle's most hostile defenses could be turned into a life-saving feast. If you look at the world's major cereal crops, wheat and corn get all the glory. But in the most punishing, drought-stricken environments on Earth, there is a grain that outlasts them all: sorghum, the catch. Nature didn't give this grain a soft, defenseless seed. It wrapped it in a chemical straitjacket. The defense mechanism here is a dense concentration of condensed tannins. You've probably experienced tannins before when drinking over steep black tea or a dry red wine. That immediate sand-like, mouth-drying sensation. In sorghum, the plant takes this to an extreme. These tannins aren't designed to kill an animal instantly. They are designed to starve it. The moment you chew raw, high-tannin sorghum, the molecules instantly bind to the proteins in your saliva, causing them to precipitate out of solution. Once in the stomach, they do the exact same thing to your digestive enzymes, locking down the grain's own nutrients in an indestructible molecular cage. According to FAO data, high-tannin sorghum can reduce your body's protein utilization by over 50%. It turns a meal into completely indigestible fiber. Yet, this exact chemical armor is what made the grain a civilizational lifesaver. Geographically, sorghum is the ultimate survivor. Originating in the harsh, unpredictable climates of northeastern Africa, it developed a physiological superpower. When a severe drought hits, sorghum doesn't die. It goes into a state of suspended animation, rolling its leaves and closing its pores to lock in moisture, waking back up the moment it rains. Furthermore, those bitter, astringent tannins served as a flawless defense against swarms of migratory birds and molds that would easily destroy sweeter grains. It was the ultimate ecological insurance policy. As it traveled along ancient trade routes to northern China, this hardy grain became the bedrock of rural survival, transforming the yellow, semi-arid plains into a reliable breadbasket. But sorghum also played a gritty, accidental role in military history, because certain varieties grow over 10 feet tall with incredibly dense foliage. The massive red sorghum fields of northern China became legendary tactical terrain. During the turbulent decades of the early 20th century and World War II, these towering, bitter crops provided perfect natural camouflage for guerrilla forces. Fighting against occupying armies, entire rebel movements moved, ate, and launched ambushes completely hidden inside the endless walls of red grain. Sorghum wasn't just the food that kept the resistance alive. It was the literal topography of their defense. To unlock the true energy of this stubborn grain, humans had to learn how to bypass its chemical defenses through mechanical and chemical ingenuity. Since the highest concentration of condensed tannins is held within the testa, the thin layer just beneath the outer seed coat, the first line of attack was simple mechanics. Humans perfected the art of aggressive dehulling and milling, physically polishing the grain to scrape away the bitter defensive exterior, leaving behind the clean, safe starch inside. But ancient communities in Africa and Asia also discovered a brilliant biochemical shortcut using basic kitchen chemistry. When cooking high-tannin varieties, they added wood ash or alkaline lime water to the pot. This subtle shift in pH alters the electrical charge of the molecules, completely shattering the grip between the tannins and the proteins, instantly releasing the trapped nutrients. Finally, humans mastered the ultimate transmutation, microbial fermentation. By crushing the grain and subjecting it to wild yeasts and molds, we developed everything from traditional African sour beers to China's legendary national spirit baijiu. The fermentation process breaks down the complex tannins entirely, turning a bitter, stomach-churning survival crop into a sweet staple food and the most consumed alcohol on the planet. Once again, by understanding the boundaries of plant chemistry, our ancestors turned a biological prison into a multi-billion-dollar legacy of survival.